Okay, yeah, thank you for coming to my talk. So I will eventually talk about graph limits, but so the title of the talk is, so we give a characterization of functions with vanishing averages over product of disjoint sets. So it's an analytic question. So let me start by asking you an analytic question. So let's say I'm given a function f over 0, 1 to m. M is some integer to c. And I'm told that f has this very nice property that if I integrate f over subsets of the 0, 1 interval, product of them, it vanishes. In fact, for just all, that's, let's say, measurable subsets. So what is f?
0.
Yeah. So it's very simple to see that f must be 0 almost everywhere. So we will, whenever we talk about such functions, we will talk about Lebesgue integrable functions f that are over the 0, 1 interval to the m. And we will be given such properties throughout the talk. We want to understand such functions. So this was an easy question. The reason that f is 0 almost everywhere is that if I pick almost every x, I can kind of differentiate around that point. And by the Lebesgue differentiation theorem, then I get 0 almost everywhere for f. But so what if I relax this property? So what if I only allow you, so this is question 1. So what if I only allow you disjoint sets? And well, the same thing, right? So f is 0 almost everywhere because so for almost every point x in 0, 1 to the m, we can actually choose those balls around them to be disjoint. OK, so finally, I want to give you a refined problem.
I mean, disjoint, when you say disjoint, they are in different dimensions, so it doesn't seem to matter.
No, so these are subsets of 0, 1 interval.
Yeah, but I mean, they are in different dimensions in the second question.
Yes. Yeah, but it's a more restricted. Yeah, exactly. So you can't argue for the diagonal f is 0, but you can. The refined problem is the following. So what if not only I ask you for them to be disjoint, what if I also fix the measures of them? So I prescribe the measures. So I'm given f, C, and I'm told that f vanishes over products am, let's say dx. And I'm also ahead of time. I'm given a set of reals, alpha 1, alpha m, in the 0, 1 interval such that some alpha I is less than or equal to 1. So what if I tell you that f vanishes for disjoint measurable sets A1, AM with respective measures that are alpha 1 up to alpha m, where mu of AI is alpha I. So what does f look like? It's a general question. It's vague what we even need from you as an answer. It certainly is interesting in its own as an analytic question. But where it came from was, in fact, Janson and Sos asked this question in the study of quasi-random graph sequences. So they were interested in proving properties that define quasi-randomness for graph sequences. And somehow, interestingly, you end up wondering about such things. But
so the zero is really, there will be a difference of two functions. One, we want to really argue about closeness of two things. Or not.
Eventually, eventually it will be that the function that you put in here for the applications, it will be related to homomorphism density of some fixed graph in your limit objects, and you want to show that that limit object is the constant p function. So it would be very nice for the applications if the answer here would be that f is 0 almost everywhere. But it's actually not hard to see that that's not true, even without going into details. But the question is, what can we deduce? What structural property?
Can you give us a simple example?
Yes, I will give you like two-dimensional examples, very simple examples. But the question is, so that doesn't stop us from, so if we have a nice structural properties of f, then maybe we can actually look at the structure of graphs. And so, well, because I want AIs to be disjoint, so it would be so f would be any function. Okay, so yeah, so I will take a very long detour now and just leave this analytic question out there. It's just how it arises. So the questions in the quasi-randomness that they're asking for is, so I will take a detour and actually talk about some background. So some introduction to, so what are random graphs, quasi-random graphs. And quasi-random graphs. And yeah, I will talk about how you can use graph limit theory to actually understand some questions about quasi-random graphs. So I will talk about what graph limits are and talk about the useful results that have been proven in the graph limit theory that we might need. And finally, now I will come back and give you a solution to the problem. Problem, in fact, once we see the graph limit, how the graph limits can be used to answer questions about quasi-randomness, then you will be able to see where this question comes up, and then we will answer a structural properties of what the structural properties of f look like, and then we will see some corollaries. So we will see how they can be used to reprove several known quasi-randomness properties, results of Janson and Sos, and in fact answers a few conjectures. And the nice thing about this theorem is that the applications are quite immediate. So you get very, very simple proofs of things that could take a lot of hard work by just plugging our theorem in there. Okay, so what are random graphs? So random graphs are arguably one of the very important concepts in modern combinatorics and computer science, where we have a model of how to generate a random graph, and we study the properties of, like, so what do the certain parameters of random graphs look like, what's their chromatic number, etc. Perhaps we can say that a systematic study of random graphs was started by work of Erdős and Renyi, where they also introduced different distributions on how to generate random graphs, one of which we all refer to as the Erdős-Renyi random graph. And the importance of these concepts leads us to ask several questions about the randomness that we need. So what are the essential properties that random graphs have? And in fact, so how can we check given deterministic graph behaves random, so this is important in many cases. So if you're designing an algorithm that uses a random graph, or if you have a proof that uses a random graph, it would be really nice to know, in fact, what deterministic graphs have the similar properties. And this is the question that actually leads to the study of quasi-random graphs. So we essentially define a graph G is quasi-random if it behaves like, let's say, the Erdős-Renyi random graph. GVP, where P is the edge density of your graph, right? E of G over G2. So the Erdős-Renyi random graph is a random graph on V vertices. For every pair of vertices, you put an edge with probability P. It's independently. And the probability of seeing a specific graph G is going to be P to the number of edges times 1 minus P to the number of edges. So this is a vague definition because I put a behaves here. So what do we really mean by this? Yes, yes. So we pick a random graph on the same number of vertices as G, and we want to see, does G actually behave like this random graph? Does it share different parameters? Of course, there is a very large number of choices for what to pick, what parameters to pick. And more generally in mathematics, whenever we want to talk about pseudorandom objects, it's really hard to come up with a unified way of defining what a pseudorandom object is. However, graphs turn out to be a bit different, and many definitions that we pick turn out to be somewhat equivalent. In particular, Thomason we could say that initiated a systematic study of quasi-random graphs. And use the natural property of the random graphs, which is their edge distribution, as a definition of randomness. So he called this, yes, jumbled graphs. So what do I mean by the edge distribution? So we already know that if I pick a Erdős-Renyi random graph on n vertices with probability P, its expected number of edges is going to be exactly P. So the edge density will be exactly P. And more importantly, with very high probability, you're concentrated around P. But this also holds for subsets. So the edge distribution property of GNP is the following property, that for all subsets of V, the number of edges of G and P in U is very close to P times U choose 2. Okay. And we could pick this, and Thomasson picked this as a definition of random graphs. So more formally, he defines a graph G to be P alpha jumbled if for all U subsets of its vertex set so the difference of the number of edges in U from the graph G from what you would expect from a random graph is bounded by alpha times size of U. Okay. So this is one definition, one formal definition of what we would pick as a quasi-randomness. Quasi-randomness condition. And however, you can do many other things. For example, Noga-Alon defined quasi-randomness based on the spectrum of the graphs. Or you could... had the eigenvalue. Okay. Yeah, so much before Alon even. So you can define randomness based on the eigenvalue gap, the gap between the largest eigenvalue and the second largest eigenvalue. You can define it based on the edge expansion. And it turns out all of these are somewhat related up to changes in the parameters.
You want it to be, but I'm not sure about your scale.
So you can pick alpha. You could, yeah. So random graph will be a root Pn jumbled. So you will have alpha can depend on n. So the parameter alpha is not a constant, so it can depend on n. The size of the graph. So you could have like alpha is something like root P size of V is what a random graph would satisfy.
Yeah. You look at all the subsets of vertices. You want this condition. You want it in every subset. You get what you expect.
Yes. So if
yeah. With the appropriate parameters, if there is concentration, 2 to the n is not so large, given if you allow deviation that's proportional to the variance.
But we already see that it is delicate when we want to define quasi-randomness for one specific graph. So another path that we could take is to talk about graph sequences that are growing. And there we could talk about asymptotics instead of having specific error terms. And that is exactly what Chong, Graham, and Wilson did in their very important paper in the 80s. So they studied quasi-random graph sequences. So in this context, we have a graph sequence Gn, and we assume that the vertex set grows. So we assume that B of Gn goes to infinity. So a very remarkable thing that they proved in their paper in 1989, is that several definitions that you could come up with turn out to be exactly equivalent. So several asymptotic quasi-randomness properties that you could define turn out to be equivalent. So I think they had 7 different definitions, but let's look at a few, one of which that will be important for this talk. So the first one is somewhat similar to the edge distribution. So it says that for all x, y, bgn, the number of edges that crosses xy minus what you would expect from the random graph is asymptotically p times. It's actually equal to, it's little of.
No, they don't have to be.
Yeah, they don't have to be.
You count edges when the first vertex is in x and the second.
It's going to.
Yeah, they can actually intersect. Yeah, so and here you can already see how this is much weaker than jumbledness. So here we allow whatever that converges to the right number is sufficient. So if you pick small sets x and y, it's always satisfied because the number of all pairs is little of n squared. The second property that turns out to be equivalent is based on the density of homomorphisms of fixed graphs. So let's say I'm given a graph f that is fixed. I want to define the quantity tf of gn. So this is going to be, okay, let me actually write it down here. This is going to be the probability that if I pick a mapping from vertices of f to the vertices of gn, and this doesn't have to be injective, the probability that this is edge preserving. This is a homomorphism. So the probability that if I pick a map from v of f.
F is a graph.
Yeah, so
you should think of it as small as a fixed size graph.
yeah, so let's so f can be like triangles or edges. I will give a few examples to make it clear. Probability that such a pi is edge preserved.
So F might have to F, but there can be more F in the image.
Yeah, exactly.
Yes,
yeah.
yes.
It's not in those. Yeah.
Yeah, so it's not in.
The number of
So
copies of F.
so for example,
Injectivity, but if F is loud, it will be injective. So it's not in the proportion of copies of F in the big graph.
yeah, so when f is a small graph, I can just draw the graph in here. So for example, the homomorphism density of an edge in a graph G is going to be 2 times size of the edge set over v of g squared. Because, so we want this map from these two vertices to vertices of G to be edge preserving, and for each edge we have 2 different choices. And the number of all maps is v squared. But note that this is asymptotically the same as v choose 2. And this is also important that when you're talking about graph sequences that have growing vertex set, it really doesn't matter whether you're taking injective maps or non-injective maps, because the probability of mapping 2 vertices to the same vertex is going to be always little O of what the number of general maps are.
Much nicer to have independence in the choices.
Exactly, yes. Or another example, I mean, we don't really need much more examples. So another way of defining quasi-randomness is the following. So we observe that if I actually pick the Erdős-Renyi random graph, and I pick a fixed graph f, so I'm picking a random sequence of graphs with the growing n. This converges to p to the e of f with probability 1. And in fact, because there's countably many graphs f, you can actually say that for all f, this converges with probability 1. So this is a very important property of random graph sequences. And we could use this property as our definition of quasi-randomness. So we say that Gn is quasi-random if for all f Tf of Gn converges to p to the. Okay. So here it's much nicer. We didn't have to introduce error terms and so on. Asymptotics. And finally, very remarkably, they showed that. So here we are checking. We're making a definition that checks for countably many, infinitely many graphs, something must hold. But the point is that you don't really need to check all of that stuff. You only need that T of edges in Gn converges to P and squares, as Avi pointed out. So there's only these two simple graphs are sufficient. Right? So that's, yeah, so the first time someone sees this, it's very nice. In fact, I will show a proof of this, a very short proof of this later in the talk. Okay, so one important thing here. So after just seeing this, one might get way more optimistic and ask, so can we actually do better than this? And the answer to, so can we do, is there like one graph f that if we fix that? So the answer to that is no. But first, let's see, is there actually, what's that?
That's easy to see.
Yeah, we will also see that.
That's a paper of yours, no? So that there is no single graph.
No, this is just, yeah, it's a simple observation. And we will see once we come to graphons. But so what are there constructions of such things? So it's important for the applications to have constructions of quasi-random graphs. Note that from here on, I've been talking about dense graphs. So most of the things that I defined, if your graph sequence is sparse, it has little O of n squared edges, they are all already quasi-random by these definitions because it just doesn't make sense that everything converges to 0.
We should think of P as fixed.
Yes, so P is fixed. And in applications, so in computer science, we are in many cases interested in P that's not fixed, that goes to 0. And those are sparse random graphs. We know them as expanders, and they have many applications. Complexity.
They are analogs of the theory with less known.
Yes. So one example of dense quasi-random sequence are the Paley graphs. So the Paley defined on prime number of vertices. So we pick a prime Q that is equal to 1 mod 4, and you define, let's say, P Q. So the vertex set is going to be the field of Q elements, and the edge set is defined the following way. So we connect x and y with an edge if their difference is a quadratic residue of Q. Okay. So we say E is the set of all x, y such that there exists A in FQ star such that x minus y is equal to A squared. And in fact, this is not a directed graph if you have chosen Q to be 1 mod 4 because minus 1 is a square. And so it turns out that the Paley graph is quasi-random with P equal to 1/2. Okay, so that's one example.
The proof is using the veil character.
Yes, yeah. So having these things, so one approach and one thing that is important to prove in the study of quasi-random graphs is what properties do define quasi-randomness. So we already saw a few examples. And in most of the proofs, there's different approaches to proving these things. And the first one is the regularity lemma. So it's the use of things like the Semerides weak regularity lemma, Semeride regularity lemma, or perhaps the Friis-Cannon weak regularity lemma. So let's say I want to prove something like this is equivalent to the number 2. So also importantly, so this is going to be our definition of quasi-randomness for the rest of the time.
The end work with b the parameter, would be the function of n.
I mean, you can define it, but I'm not aware of the non-dense.
Number 3.
So the only thing I know is that we understand much less, but
Number 3 will not hold because
Yeah.
it's not I mean, you see that the number 3 will give you an eigenvalue estimate, but it will
So-
just
so in particular, you can't normalize by the number of mappings. That's what I just said, right? So, but you maybe want to somehow have a better normalization that gives you a non-zero limit. Yeah. So in the application, Semeride regularity lemma allows you to approximate a given large graph by a somewhat smaller graph, which is multipartite, and between every 2 parts you have a random graph. So you have bipartite random graphs. And when you apply this to the graph sequence, it reduces the problem to like algebraic problems. So because now you have these multipartite graph, and between them you're random with different densities, like P1, P2, etc. And let's say someone tells you that so this bigger graph has this density of triangles that's p cubed. Now it's kind of an algebraic problem. You can actually rewrite the density of triangles based on this number of edges, and you maybe can prove that all of them must be the same. Things like the second approach. But one thing that we immediately see if we're trying to do it in our mind is that it's very delicate often. And you have to deal with a lot of error terms. So you have to approximate your first graph with this partition, and then you have to. The second approach, which is much nicer to work with, in my opinion, is the graph limits approach. As the name suggests, here we want to take the limits of our graph sequence. So we are talking about asymptotics of a graph sequence. Why not? It would be really nice if we could take their limit, and we already know that there is a very rich theory of graph limits. So the approach here is to translate the conditions to the limit object. And this often allows analytic arguments. Which are much cleaner in many cases. And in several cases, it's not even clear how to prove it in the finite tree version.
When you say translate to limit objects, do you mean, when you began,
You
began with kind of a finite fixed thing. There wasn't an obvious sequence.
Yeah.
At all. So do you mean the translation of a finite problem into an infinite problem?
So from here on, I stopped talking about one single graph. So now I'm actually talking about properties of an infinite graph sequence.
Okay.
Right?
You will have to explain what is the limit object.
Yes. Okay.
But this theory, the 10 years.
Yeah, maybe like 2004 was when we. Yeah. Yeah. So let's do that. Right? So. Yeah. So, what are graph limits? So the first thing we need to know is actually, let's forget about the limit object. When do we actually say a graph sequence converges? And that's not hard. So we can use kind of same definition, but not with the p to the e. So we define quasi-randomness to be the fact that for all fixed graphs, the homomorphism densities tend to p to the e. We say that a graph sequence converges if they all converge, not necessarily to p to the e, to something. So that's going to be our definition. So we say a graph sequence Gn with v of Gn going to infinity converges if Tf, if for all f, Tf Gn converges to some limit.
The convergence of the structured object into a sequence of numerical, not standard numerical.
Exactly.
Converges as of real.
Right, so we don't really know what it converges to. So we actually, the way that we're defining it is, so each graph sequence that is convergent defines, let's say, vector of densities that for each f, you have an entry. This is the number that it converged. So it would be really nice to actually find objects that realize this limit, right? And
So what kind of limit object can one?
so these are called graphons, and we will see in maybe a few lines. So but the first things that were observed are that you can't have a graph, a finite graph that represents this number, because these numbers can be any real numbers. And moreover, it was observed that even finite weighted graphs, vertex and edge weighted graphs, can't realize. So there are examples that you can construct that even weighted graphs don't realize it. But Lovas and Szegedi in yes. Okay, I messed up the whole name. Is this okay? So as Avi suggested, this is not that old. So they constructed these limit objects, and they look like the following thing. So they're called graphons. And they look like the following. So they are functions from 0, 1 squared to the 0, 1 interval that are symmetric and measurable. So first of all, let's actually see what the intuition here is, right? So every finite graph has this adjacency matrix, right? So it's an n by n adjacency matrix where we put a 1 if they're connected or not. This kind of, you can think of it as a continuous graph. The 0, 1 interval is its vertex set, and it's a weighted graph. So for each pair of x and y, you put a weight. So how it looks like is you have this 0, 1 box. That's its continuous adjacency matrix, if you will, and you fill it in with maybe it's zeros up here. It has some values here. Maybe it gets denser as you get closer to 0, and so on. And so this is the way that they're defined. But we still need to define what it means. So we wanted these to represent our limit objects. So we need to define what actually the density of a graph in a graphon is. But it's not really hard. It's very straightforward to define them. So instead of taking the probability, we integrate over the vertices. Okay, let's do that. So for a fixed f, we define Tf in a graphon W to be the integral df of what you would expect. So we kind of look at it as an adjacency matrix. So we pick ij in the edges of f, and we put w xi xj dx1. So this is going to be our definition. So we are basically picking the first vertex in the 0, 1 interval, second vertex. And over all of them, we look at the weight of the map from the edge set of f to wx, xi, xj.
Partition functions is a good intuition. That was one of the original motivations.
Yeah.
So in particular, T of the edges in W is really integral of, it's just the L1 norm. Of your graphon. And it also is not hard to see that these graphons are in fact generalizations of graphs. What do I mean by that? I just defined this new set of objects that look like they're continuous, but my graphs are not in the set. But for every graph G, you can construct a graphon WG that has exactly the same properties. And that's not hard to at least see by an example. So let's say G has n vertices. What I will do is I will partition the interval into n parts, and I treat each of the intervals of length 1 over n as a vertex of my graph G. So I get this grid, and now what I do is I look at the adjacency matrix of G and fill in the entries that were 1 with 1. So I put a 1 wherever through the whole box, if there was an edge. In particular, if G is a simple graph, the diagonal is 0, etc., etc. But this is WG, and the important property is that Tf of G is equal to Tf of WG for all G, for all F. Okay, so it is in fact a richer class of objects, and there are so whatever you would desire from a limit object, Lebesgue and Szegedy have proved since. So one very nice property is that, in fact, every graphon that you pick is the limit object, is the limit of some graph sequence by the definition that we picked. So they proved that Lebesgue, Szegedy proved that for all W there exists a graph sequence such that Gn converges to W. And I won't tell you the proof, but it's actually very nice. So it uses a fact. So I'm given this continuous 0, 1 interval by 0, 1 interval function. So let's try to generate random graphs using this as a guideline, random graphs that look more and more like W as we increase the number of vertices. So they introduced this idea of W random graphs. Exactly. So the Erdős-Renyi, you just pick every edge with probability P. What you do here is
the Erdős-Renyi graphon is a constant function W which has value B everywhere.
Yes. So under this definition, the Erdős-Renyi will be W, which is the constant P random graph. So if it's on n vertices, what we do is we pick x1 up to xn uniformly from the interval. Pick these, and then connect I to j with probability wxi xj. Okay. That's a very nice process, and what makes it nice is the fact that TF of W is always concentrated around TF of, let's name that Wn on n vertices. So in fact, the concentration is exponential, which allows you to use like Borel-Cantelli and show that with probability 1, it will converge to the right thing for all f. Okay. So that's how this theorem is proved. But in fact, they prove more. They prove that for every convergent sequence of graphs, there exists a graphon such that Gn converges to W, which is this is exactly what we wanted. Every graphon is the limit of some graph sequence, and every graph sequence converges to some graphon.
This is a compartment theorem.
Yeah, right. So in fact, yeah, what they prove is that also a space of graphons is compact, meaning that every graphon sequence has a convergent subsequence, and in particular, because we already saw how.
Yeah. So,
Okay.
very good question.
Great.
You're
I can tell. So there, you can define a norm for graphons, and in fact for the space of all kernels, which are not 0, 1 but minus 1, 1. So it's the cut norm. So it's you can define a norm on the space of graphons, which is defined. I will define it for a graphon and then tell you how you define the distance. Is defined as the following. It's the supremum over all subsets of the measurable subsets of the interval 0, 1 of so this actually is a norm. And in fact, we can define the distance of two graphons. However, one has to be a little bit careful, because the way we're dealing with graphons is we only care about density of subgraphs. And you can have two different graphons that have exact same density, but they're not the same function. So in particular, you have to get rid of all the null set differences. So we will say that W is equal to W prime if they're different up to a null set, but also if they're different up to a measure preserving map from 0, 1 interval to itself. So when you're
rename vertices, so you can rename. Like,
yes, exactly. So you can permute vertices of the graphs.
We saw us doing this proven by
and you just want to next myself.
So you define the distance of W from W prime to be the infimum over all invertible measure preserving maps from 0, 1 up to 0, 1 of that of W minus W.
And you need that to have capacity.
You need what?
To do this to have capacity. You don't have capacity.
Compartments?
Yes.
Yeah.
Yeah. And as I already, so through this discussion, we already talked about how it doesn't matter if you rename the vertices. And it also doesn't matter the way we define the limit object there. But what is important is that this discussion, the way the compactness is proved, also tells you that if a graph sequence converges to two different graphons, they will be weakly isomorphic. So you can't be convergent to two graphons that are very different from each other.
Probably you would say that separate regularity lemma is hiding it, or is equivalent.
At least so the Fries-Conan weak regularity lemma is, as you can see, is related to the cut norm. Even in the finite version, lies in the proof of compactness, and you can deduce summary irregularity lemma from compactness. Yeah. So they are equivalent statements. Right. Yet another nice property of introducing this space of graphons is the spectral theory of them. So recall that for finite graphs, we look at their adjacency matrix, and we look at it as a linear map from Rn to Rn, and then you can actually talk about eigenvalues and so on. But you can also look at W and define a Hilbert-Schmidt operator out of W, which is, let's say, maps L2 of 0, 1 to L2, 0, 1. And it's defined the following way. So TW of a given function in L2F, L2, 0, 1 interval at x is defined. So we integrate over y w x y d of x. Okay, so this is an operator that you can define, and it turns out dy, yes. Sorry about that. So and it turns out that such operators have a very nice discrete spectrum where each eigenvalue has finite multiplicity. So we say that something is an eigenvalue, same as the matrix case. So we say that lambda is an eigenvalue if there exists some f such that twf is equal to lambda f. Right, so that's when we say lambda is an eigenvalue. In particular, this allows writing W, so writing its spectral decomposition. So let's write it as a theorem. So we can write every graphon one. You can write its spectral decomposition, which is of the following. Okay. Fk of x infinity. And these are the eigenfunctions, and they have L2 norm 1, and they're orthogonal to each other. Okay. Yeah. I only know the consequences, but yeah. Yeah. I learned this from the Lovas's books. And the reason I'm telling you is not just to add a story. We will actually see how this can be very useful. So one very useful thing that you could see immediately, just using the eigenvalue decomposition, is that if I look at things like density of Cn, the cycle of length n, in your graphon, this is exactly the sum of the kth powers of eigenvalues. Right? And this even works for, and here you just basically plug in the expansion and use the orthogonality. And this even works for a cycle of length 2. K squared. Okay, so we talked a lot about graph. Sorry?
How can you have multiple edges in something?
Well, it's not a simple graph, but you can define it, right? So you can define this as.
Because you don't think of it as symmetric, or it could be
It's
not
symmetric.
symmetric?
It is symmetric, but the diagonal is, I mean, you can, because of the
So
way.
it's the same as having one edge.
No, so you treat them as different edges, and when you're taking, so this is equal to the 0, 1 squared of wxy squared. So between x and y, there are two edges, so you have a power of 2. Right, so you just, I mean, that's how, it's just the definition. dy. And
All of this was important to graph were not direct. I guess.
Yeah.
Because
yes,
it was,
it is, yeah, it is very important.
So what's the meaning of this equality, wxi equal? So in what sense of convergence?
Well, so this is convergent.
In what sense of
In almost everywhere convergent. Yeah, yeah. And the two terms are equal. Yeah. Yeah, again, so you should have almost everywhere, because I can mess up W on an all set.
the other notions of convergence?
so in two words,
Sorry?
I would hope and do convergence is true.
Perhaps. Yeah. Okay. But let's see how the graph limits are useful. And so go back to quasi-randomness, and I will prove this theorem. So yeah, so we will see how this implies number 2. Right. Thanks. Okay, so we want to prove that part of the theorem by Chang, Graham, Wilson that says that number 3 implies number 2. Right? But I want to use the graph limits. So what does the theorem say? It says that I have a graph sequence such that the edge densities and the 4-cycle densities converge to p and p to the 4. And I want to say that for all graphs f, the density converges to p to the e. But the problem here, at least at the first glance, is that no one has told me that Gn converges. Right? So I can't just pick the graphon and go on. But the point is that we already saw that the space of graphs is compact. So I can assume for contradiction that number 2 doesn't hold. So assume 2 is not true for some f. And this already implies that there is a convergent subsequence of Gn for which Tf of Gn doesn't converge to the right number. So there exists, let's say, Gm, which is a subsequence that converges to some W, some graphon W, and I know that W is not p to the e of f. Right. And I will deduce the contradiction from here. I will show that actually W has to be the constant p. But how do we do it? And the proof is really nice. It involves 2 Cauchy-Schwarz inequalities. So let's see it. I start from this quantity, which I'm told by the theorem that it's p to the 4. Because the original sequence converged to this, so the subsequence must converge. But I can rewrite the following way. So this involves integrating W, picking x, y, z, and w, and then looking at the density of 4 cycle. What I can do is I can first pick the 2 vertices on the diagonal, name them x, y. And look at the following quantity. Why is this true? So first of all, what does this mean? It means that now I'm integrating over this empty vertex where x and y are already fixed. That's true because once I fix these two, I'm interested in the density of this guy and density of this guy, but they're exactly the same because you're integrating over the whole interval. So now this allows a Cauchy-Schwarz inequality. Squared. And we will do the same trick again. But now, note that this is really what this quantity is. I picked these 2 vertices and then integrated over this. I'm just looking at the density of path of length 3. And I can, again, first do the mid vertex and then look at the other 2 vertices. So what this is really is the following. It's integrating over z, t of z squared. But again, I can do another Cauchy-Schwarz here. So this is that notation. Finally, I get this quantity. Yes, what is this? This is really you're integrating over both of the vertices of an edge of the density of in W, and we are already told that this is p to the 4. So what happened is the left-hand side and right-hand side are the same quantity, so the Cauchy-Schwarz, you have the equality case of Cauchy-Schwarz for both Cauchy-Schwarz, but I will pick this inequality to look at. So what this implies by the equality case of Cauchy-Schwarz, this implies that xyw doesn't depend on xy, at least almost everywhere. But what is this quantity? This is w z of w x z w zy dz. This is exactly this quantity. Okay, so what's the next trick? Okay, so this is the next trick. I will plug in the eigenvalue decomposition of w here, and I claim that this really equals So why is that? So if I plug in that sum for both of these terms and I multiply it, I get terms that are of the form fk of x, fk of y, fk of z. Okay, let me just write it. So we get the following thing. We get wx wzy is equal to k and j lambda k lambda j, fk of x, fk of z, fk of j of z, fj of y. And here I'm integrating over z, but if you integrate over z, everything where j and k are not equal vanish. So what you get is really this. But I know that this is the constant function. That was the nice part of it. So I integrated the square of something that was a constant, and it was p to the 4, so it is p squared. So this already implies that w itself must have been the constant. So it has the only eigenvalue of w itself is p. So this. So that's the one nice way of proving the Chang-Graham-Wilson theorem. And of course, that's not how they proved it. This is using a lot of machinery that wasn't there back then. But let's go back to the question that I was asked. So what if I want one graph instead of two graphs, edge and the 4 cycle? So here's a nice way of saying that it doesn't work. So so the question is, does there exist some f such that tf of gn converging to p to the ef implies w is a constant p? Okay. And we already saw the reason that I'm assuming that it has a limit is from the proof we saw that we can really deal with the subsequence that's convergent. And the answer is no, and the construction is the following. So if you give me a graph f, what I will do is, let's say I look at, so let's say I pick a parameter a, put everything else 0 in my w, and here I put everything to be some b. What's the density of tf? So I will name this WAB. So tf of WAB is equal to, first of all, as soon as you pick some vertex outside here, you're done. So you have to pick the vertices inside. So I will assume that the graph is connected. So you have a to the v of f. Just to normalize, you have to pick all of the vertices here. And once you do, then you get p to the e of f. B to the e of f. So that's the density. Yeah. Yes, so I assume f is connected. Yeah. But now you have so much freedom. So all you want is that this is equal to p to the e of f, and that a is between 0, 1, b is between 0, 1. As the only case you can't deal with is when p is 0 or 1, right, which are the trivial cases. So that there's, in fact, infinitely many counterexamples. But this didn't still, this.
You show that if you choose different a, you get something.
What's that?
Yeah.
No, you can increase b and decrease a, right? Yeah.
There is some other book that is not.
What's that?
It's obvious they are not equivalent.
Okay.
Right.
You cannot compute the names of vertices to get them.
Yeah.
It's two intervals that are different size. So if you measure preserving. So the question was that, so these WABs for different A and B, can they be weakly isomorphic? And yes, you have to argue that, but it's not hard to see. So what people actually...
Now you can ask what other graphons you can determine by 2.
No, in fact, people still ask, so what can we do with one graph? So yes, so it didn't work this way, but can we have some stronger property that with one graph that defines it? And here's an example of a positive result in this direction. Shimonovich, and Sos proved that, well, it was not enough to look at the whole graph, but if I look at restrictions to measurable subsets, and this is equal to p to the e of f, this always implies that the limit graphon is almost everywhere. So this, in fact, works for any graph that's not empty. So this is for all f that is non-trivial. If I look at all restrictions of f to measurable subsets and look at the density of f, and it's the right density, then I'm done. Of course, so this looks like the edge density property, right? So you're looking at these restrictions, and instead of looking at the edges, you're looking at f densities. So that's not very surprising. But let's see a much simpler lemma. So this is somewhat complicated to prove. I will definitely not be able to prove my own result. Okay.
Always speak next week.
So this is due to Yanson. It's an observation. It says the following. It says that Gn to W is quasi-random if now we slightly move toward where the talk. For all A1 for all subsets of the 0, 1 interval for each vertex, I know that so I'm looking at the density of f in my graphon. F, but I have to also normalize by the measures of. So this is what the observation was. So it says that your graph sequence converges to some graphon if I tell you that for every collection of subsets of the interval this equality holds, then it implies that W is constant, P. But it's a much, much stronger. This is very strong. So here you only pick AIs that are the same. But the proof of it is also very quick. Here's the proof. Define a function from 0 m to the complex, to the real valued function even, to be the following. xb is this quantity minus p to the e. Okay. Well, now this is a function that does vanish if you integrate it over any collection of the measurable subsets of 0, 1. And we already saw that f must be 0 almost everywhere. So we already saw as an answer of question 1. And there's still, we are not done, because what this says is that for every x1 up to xv, this quantity is equal to p to the e. But what we want is that w is equal to p almost everywhere. But Janson, in fact, proved a lemma that's very useful. And he showed that this is always sufficient. As long as f is a non-empty graph, it's always sufficient to show that this difference is 0 almost everywhere. If this was 0 everywhere, then it would be really simple to deduce w is, in fact, P.
What is the subtlety? Can you explain?
Well, so now I want to go from here to show that Wxy is equal to P almost everywhere, right? But I have something that's still not quite simple. So if it was everywhere, then you could actually do nice things. You could pick x, like one vertex and map it to x and map everything to y. And you would have that the power of Wxy is equal to P to the E, things like that. But the point is that as soon as you start arguing things that pick something from diagonal, then those are measure zero sets. But what he showed is that if you have a graphon that satisfies this equality almost everywhere, there is a version of that graphon which you change it by a null set, and that satisfies it everywhere. And then you would be done. But so for the rest of the talk, whenever I want to prove that W is equal to P, we will stop at this step. We will just show that F is. And now you can see where the motivation of asking this question came from. So they tried looking at different graphs and seeing if they define quasi-randomness, and they all lead to trying to understand such functions. In particular, Euster, Shapira, and Janson and Sos defined the following definition. So they said that a graph sequence satisfies Pf alpha m if exactly that holds. So if, but for the graph density, Am, let's see. Sorry?
M and N should not be the same.
No, actually, so this is the number of vertices of F.
Sorry, M is the number of vertices.
Yeah, sorry about that. Yeah, so V of F. And I have to normalize by the densities. Is equal to P to the E of F. And this holds for all disjoint zero, one of measures so that's, they asked for, and this is the question they asked. So for what combinations of F and alpha 1 up to alpha V, this defines a pseudo-randomness. So M P alpha implies W is equal to P. Okay, so that's the question.
So far W was real value.
It is real value. 0, 1.
The question you asked for the complex.
Right. So motive, and I mean here you can already also see that if we are only interested in answering this question, this is too general of a question to ask because F is very complex. Here the F that I'm interested in is defined using a two-dimensional function that's symmetric. Right? So it's, namely, it is the difference of this quantity and P to the E. So these are very structured functions. And in many cases, maybe it's easier to, and that is in fact what allows us to show that F is 0, let's say, in some examples. But yet they asked for this question.
Just a two-dimensional example when it's not.
Okay, yeah, that's I can give you an example at this point.
Half and half.
Sorry? Yeah, so in fact, there is a counterexample to this, which is an edge. And again, so this goes back to Chang, Graham, and Wilson, who showed that P of a single edge and half doesn't imply. So what's the counterexample? So let's do it. And we will see generally why this actually counterexample method makes sense. So I will pick a function g from 0, 1 interval to -1, 1 interval, such that if I integrate g, it vanishes. Okay? Sorry?
It's not just a difference.
Because, right. So I will just define g to be this one variable function. And I will take w x, y as the following quantity. P plus some epsilon gx plus some epsilon gy. And I will pick epsilon small enough such that p plus this quantity never is outside 0, 1 interval. Right. I claim that this w, even though it's not the constant p function, satisfies p of edge and 1/2 and half. Why is that true? So all I have to show is that if you pick a partition of the 0, 1 interval to two sets A and B, and if you look at this is equal to p times this is what I want to show, 1/4, right? But it's not hard to show, because if I look at w minus p and I integrate it, so this is a partition, and their measures are 1/2 and 1/2. W minus p is really equal to integral ab epsilon g of x plus g of y dy. But gx doesn't depend on b, on y, and gy doesn't depend on. So this is really equal to 1/2 epsilon integral a gx dx but now this is integrating over the whole interval, you get 0. So that's just I don't know what it looks like for finite graphs. But, so this is, you can construct many, and by the lowest security, their limit of some graph sequence. But yes, yeah, I'm not sure. I haven't thought about.
No, I just need to find particular g.
I haven't read the Chang, Graham, Wilson proof, but I assume that they have constructed a graph because they didn't deal with. But we will see that this was actually a natural way of constructing if you're looking at the graphons. Okay, finally, I will talk about our theorem. So we answer that the question 2 or so. 2. So what we do is, this is a joint work with Hamed, Hatami, and Yaqiao Li. We give a characterization of such functions based on their generalized Walsh expansion. But okay, again, so before I can tell you what the theorem is, we need to see what we need to just review what generalized Walsh expansions are. Okay. So I'm given a function f. Complex value function f over 0, 1 interval to the m. Its generalized Walsh expansion looks like the following expansion, where you write f equals fs, where s are subsets of m. We will call these things as generalized Walsh functions. And they satisfy the following two properties. So I want to write any function f in the following expansion where they satisfy the following two properties.
You don't want coefficients.
No. Yeah. So if you were doing Fourier analysis, sort of, you have coefficients and characters, but you can bunch them together. So I want that fs only depends on xi with I in S. So fs doesn't depend on variables that's outside S. And moreover, if I integrate fs over any of its variables, dxi, again for I that is in S, it vanishes. Okay? So I just... Sorry? Yeah, I'm sure. So this has many different names. Yeah, F1 Stein expansion or Walsh expansion. So I will call these things Walsh functions from now on, and refer to this as the Walsh expansion.
Second condition, what prevents you from taking f, just taking the set, which is the whole set. Taking f.
Oh, this is for all
Yeah.
I in S.
All right. No, I mean you could take f itself as its representation unless you.
Unless yeah. And this is actually what Walsh functions are. Yeah.
Right.
So, I mean, you can construct Walsh functions. For example, one way of constructing Walsh functions is looking at characters. For example, you can say fs of x1 up to xn is e to the 2 pi I sum j in s xj. Okay, so this is a function that does satisfy number 2. But it's important that, so this exists and it's unique for every given function. F. We can see how to actually find these functions. So let's look at a 2-variable example. C. So I'm claiming that you can write f as like f empty plus yeah, so f empty is just average of f. So but once we know what f empty is, to deduce f1, all I have to do is integrate according to x2, which kills these two terms, and subtract f empty. So f I, in fact, is equal to integral 0, 1 half d x, let's see, 2 minus I minus f empty. Okay. And once you know f1 and f2, to deduce what f12 is, you subtract these two and then add f empty. So more generally, you can deduce the following formula.
Pulling back give you n orthogonal idempotent, so the decomposition space of
Sorry?
Give those operation of integrating in one variable and pulling back the result. And those are idempotent operations which commute to one.
Right. I see. Yeah, and the formula for fs, if I have an m-variate function, fs will be equal to the sum g subsets of s minus 1 to the s minus t integrating 1 to the t complement of f dx t complement. Okay? And you can check that this works. Okay, so now I can state our theorem finally. I will do it here. Maybe actually I will do it here because it's under the. Okay. I will name this property to be like star. So f satisfies star if and only if its Walsh expansion looks like what I will write here. So if f is equal to some fs, where first of all the empty Walsh function is 0. So that's not surprising. What's very nice is the following. So we get that fs is an alternating function. So yes, so what does it mean to be alternating? So it means that if I pick any two variables that fs depends on and switch them, it switches the sign of fs. So these are not the typical Walsh functions. So these are not, for example, alternating. But you can.
That's for every s.
For every s, yes. You can construct alternating functions in the following way. So for example, you could add here, say j less than k of e to the 2 pi I xj minus e to the. So now this is an alternating Walsh function. Because if I switch any xi and xj, only one of these terms will flip its sign, but it's still, if I integrate it according to any variable, it will be 0. And the third condition is a bit technical, but here's what it says. It says that if I pick any s, that subset of, so I throw out the last variable. So I just look at subsets of the first m minus 1 variables. It says that fs up to normalizations, so product of alpha i's that are in s, can be written as a linear combination of I in s. Again, some real coefficients as union m minus ith variable of f of that. Okay, so it is technical, so let's hesitate and try to understand what it says. So first of all, so on the left-hand side it's clear. I have fs, s doesn't have the last element. On the right-hand side, I have a linear combination of fs's, s primes, which are of the same size. So what I've done is, for the ith variable, I've replaced it by the mth variable, and xi is exactly similarly constructed. I switch xi and xm, and that's how I get xi. So what this really says is that if you look at each level of the Walsh expansion, everything else is determined by the Walsh terms that have the variable m. And since our theorem says this is if and only if, so this is somewhat surprising. So it tells you that if f vanishes over all such things, in fact, each layer of it, you can check that if it satisfies this, each layer of it will vanish. So one layer, the Walsh functions on one layer can't contribute to the other layer vanishing. So the only dependence that you need is this. And the way you can construct any such function that has that property is pick Walsh functions that you like and put them on the last terms, s's that have the last element, and use this formula to just find the whole definition of f.
And if you pick them alternating, the other will be also.
Yes. Yes, so what you really need is just pick alternating here and then everything.
So you just have to show us that this applies to some graph. I mean, this is just general.
Right.
But you wanted to apply it. I mean, are there any?
Yes, so there are several applications of what we can do with it. Okay. And yes, of course, I won't have a lot of time to show all of them, but let's pick a few applications. Sorry? So if I want to construct such functions, what I have to do is I have to look at the terms here where the element m is in S, right? And as soon as I identify what Walsh function to plug in there that satisfies 2 and 3, then the rest I have to fill. I'm forced to fix them. Right. Let's look at the
It's really a subspace of all.
Yes.
It's really now subspace.
Right. Let's see some simple corollary, which was the theorem of Janson and Sos. Which is the following. So if I have sum of alpha i's are less than 1, and f is a non-empty graph, pf of alpha v of f implies quasi-randomness.
So as long as you leave some room for.
Yeah, so it's not surprising, and the proof will be very simple. So what we do is exactly the strategy as before. We have this function product ij in E of f, w xi xj, subtract from it p to the ef, and define this as the function f. And I know that this, because the graphon w satisfied p f alpha 1 up to alpha v, then f satisfies what we have this here. What I forgot to tell you is, okay, that was important. That so our theorem only works when sum of alpha I is exactly 1. It's important. Okay, so we can't immediately apply our theorem here. And you will see that, in fact, the reason that this is easy is because here you can actually say f is 0. In fact, any f that has that property. So claim
The sum of alpha is smaller than 1. Does there exist any f, you think?
f is just 0 in that case. Yeah, exactly. Yeah, so sum of alpha I less than 1, I claim that that already implies f is 0, even if f is not something complicated, something simple like here. And the reason for that is the following. So I can define a dummy variable and just say this f xv. And now this function satisfies the property, and it satisfies the premise of my our theorem. So we know that. Sorry? Yeah, it's not hard to see that if you integrate it, it's up to a constant 1 minus sum of alpha i's. You're going to get 0. But okay, so what does this say? Our theorem tells us.
So you take the f sub s which contains these variables and they are 0.
They are 0. Yeah, exactly. So so first of all if I write g, so the terms that depend on the last variable must be 0 because the expansion is unique and g is equal to a function of a subset that doesn't have that. So we know that all these terms are 0, which by our theorem says that, well, all fs must be 0. Well, we're done, so two-line proofing. Because, so this implies that g is 0 and g was equal to f, so f is 0 almost everywhere.
There is something really unique about the sum of alpha is equal to 1 because I'm guessing that then you're just partitioning the interval.
Yeah, so you don't have this freedom of moving things around, for example. But no, so.
In the example that you showed the integral of a plus the integral of b was the integral of 0, 1.
Yeah.
So
Let's actually see another theorem of Chang, Graham, and Wilson as a quick consequence. So we already saw that the edge and half don't work. But I claim, and they in fact proved, that P of edge and alpha 1 minus alpha does work if alpha is not equal to 1/2 implies that OE is equal. So this is a partition and it still works. So this is an example of where things can be different. So how do we prove this? So here, if I look at f of xy, which is wxy minus p, then I get a function that if I integrate it over any partition of density alpha and 1 minus alpha, it vanishes. But in particular, now I have a partition, so I can immediately use our theorem. HHL. But now I won't use part 3, I will use part 2. So part 2 of the theorem said that your Walsh functions are alternating. So this is a 2-variable function. So f has really expansion of size 2. And we know that by part f0 is already out. So you have f1, f2, f1, 2. So I will apply part 2 to f12. So what does it say? It says that f12 is alternating. But I also know that f is symmetric. So if you're both symmetric and alternating, then you're 0. Right? 2 is symmetric and alternating So it must be 0 almost there. So we got rid of f1, 2 as well. So what can we say about these two guys? So now I apply part 3. But note that part 3, if I apply to sets of size 1, it's not this complicated. So if fs is of size 1, then all it says is you have one term here, one term there. So all it really says is that f1 times alpha 2 is equal to alpha, like not alpha 2, 1 minus alpha is equal to alpha times f2. Okay. But why is this? Sorry? Yes, yeah. So f1 is equal to f2, and we have assumed that alpha is different from 1 and 1 minus alpha. So we deduce from here that f1 is 0 almost. So putting all of them together, we get that w is equal to p almost everywhere. So we already saw an example of how this can be useful, just looking at how f looks like. You can modify this proof and, in fact, deduce that I could have more variables as long as f was symmetric. You can get that everything is 0. So if f is symmetric and you have a sum, you're given a sequence of alpha i's which are not all 1 over v. So as long as there's two things that are different, then you can do a similar proof and show that f is 0 almost everywhere. Okay, so in fact, there is an optimistic conjecture by Janson and Sos. I would call it optimistic. I don't know how much reason it is to believe that it is true, because we are far from understanding it. As you already saw, the examples and results that we have are very simple graphs. So they conjecture that P of f is the only counterexample. So basically, they conjectured that if you pick any f and any sequence of alpha 1 up to alpha v, this defines quasi-randomness. And to see how far we are from understanding this conjecture, let me tell you another conjecture from the same paper, which was implies. Yeah, so even the path of length 3, we didn't know how to deal with it. So we know how to deal with it if these two have different values. So if the alpha that corresponds to this is different. But we didn't know how to. And as a corollary to our theorem,
So it's not even known for particular.
so there are some.
One quarter. Oh, sorry. 1 quarter. 1
So
quarter,
this
1
was,
half.
in particular, for example, something that's not known is, yeah, not known. Yeah. We actually show that as long as you have two vertices that have exactly the same neighborhood, two we call twin vertices in your graph f, then in fact pf of alpha 1 up to alpha v does define quasi-random. So this is a special case. So, sorry?
That's conjecture.
What you said before.
Oh, this was conjectured in Janson and Sos, and we answered it. Yes. we answer this one. Yeah. So that's a special case. And well, I won't have time to show you the proof, but it really is, there is a hidden equality case of Cauchy-Schwarz in the proof, because you have two vertices that you can kind of, so we look at what our theorem gives us and then use that to get an equality case of Cauchy-Schwarz, which tells you this thing. Okay, finally, and in 5 minutes, I want to tell you what goes to proving that such a theorem, such an analytic question. Okay, so just a high level.
Clear from the condition that what we are looking for is the linear space, right? That the function satisfying this is.
So one direction is as you're suggesting, it's very easy. So if these are satisfied, then you can, it's just a little bit messy to write.
I mean,
Oh, you mean the other direction?
Just a high level, you are trying to characterize a set of functions.
Mm-hmm.
I mean, it's clear by the question, at least, that the answer is a linear space of functions, right? The condition is linear.
Yes. Yes. Yeah. So the argument is what they call a first variation argument. So what we do is the following. So let's say I have the point x1 up to xm in the notation of the theorem that I want to argue about, that fs on this set does alternate for almost every x and so on. So what I do is I look at the interval 0, 1 and pick sets of the right measure such that the first set, so x1 is in A1, AM. Okay? Just for the simplicity of this illustration, let's assume that they're interval. They can't be always in. So this is A1, A2. Let's say I have these points, x1, x2 is somewhere. So what we will do is the following. So I will pick a very tiny ball around each of these points. Okay. So we know that if I integrate f, I get a 0. But I can also find a few other sets of the same measure by doing the following. So pick any permutation that's your favorite permutation, sigma, and permute these balls and lend the ith ball to the ith where the permutation sends you. And this way you can define a bunch of new sets, A prime 1, A prime m, of the same measures. But you also know that f over the new set is also 0. But the point is that A1 and A prime 1 differ on two tiny balls around points xi and x pi I. So we do derivatives. So that's the idea. So what you can do is you can define like a parameter t, which is the size of those balls, and the parameter pi, and then we do sort of derivatives. So we look at this function and name it some f x and y, and we look at derivative of f dt from 0 plus. And what this really does is it allows you to get a linear combination of integrals where now you have gotten rid of one of the sets. And so you're actually getting, by again, so the Lebesgue differentiation theorem, so you're isolating at least one of the variables and you are plugging in a constant in there. So what you get here is something like some I equal to 1 up to n m of a m minus I, and what you get is really f, where now the first term you have plugged in x of pi I minus the second term you have plugged in xi. Okay, you can actually check that this works. So why is this very useful? So here you have eliminated one of the integrations. So you can rewrite this as actually a m and normalize it by 1 over alpha I, because we know what that set is like. So if we look at the Walsh expansion of f, I can take these derivatives, I can pick these derivatives in a way that's, for example, if a permutation maps this guy to itself, then this difference is 0, right? So in particular, if I'm doing this derivative, and the only things that are not identity in the permutation are things that my function doesn't depend on, what I get is completely 0. And you can use this idea and look at f, sum of fs, and focus only one of the s's.
But will it be inductive on the size of S?
Yes, so that's what the
reactive one and zero.
actually the other way around. So we will start with the largest layer. Yeah, because those are the problematic ones, right? So if I want to single out fs, I can kill everything on the same layer and the lower ones by this differentiation, but things that are higher won't. So I assume that things that are higher are already handled and cancel out, and I look at up to kth layer. So the rest of the proof is basically we will prove 2 and 3 based on 2 different kind of collections of permutations and vectors, and getting the identities that we needed. And that's all I will talk about. Thank you.